Welcome for the next lecture on artificial intelligence in robotic course, and this time we will continue on data collection planning, but we will extend the existing methods and the methods we described in the previous lecture towards planning with curvature-constrained trajectories. So we will extend the traveling salesman problem with neighborhoods, as well as an orienteering problem and orienteering problem with neighborhoods to the planning with curvature-constrained paths and trajectories that are modeled by Dubin's vehicle. So we will introduce Dubin's vehicle and Dubin's planning, and the fundamental building blocks for these routing problems with Dubin's vehicle, which we consider is the Dubin's Turing problem. Then we will continue with the traveling salesman problem with neighborhoods, orienteering problem, and orienteering problem with neighborhoods. And in principle, these problems are very similar to what we shown in a previous lecture, but the main modification is that we consider not straight line segments, the Euclidean distances, but lengths of the optimal Dubin's paths that connect to configurations with the prescribed headings. And in the very end of the lecture, I will show you some further generalization and examples. So let's start with the Dubin's vehicle and also with the motivation. So in data collection planning, we are sending vehicles to the environment to visit some locations of interest, to collect data, take measurements. And if we consider area vehicles, such as fixed wings, or even multi-rotor vehicles, we should prepare a path, the data collection path, that is feasible and for the vehicle and the controller that follow this path or trajectory is able to follow this trajectory with sufficient precision. That's particularly hard for these multi-rotor drones, but if you consider this fixed wing vehicle, you cannot actually move arbitrarily. You actually need to follow some minimal turning radius to take a turn, which is related to the velocity. And similarly to any data collection planning we discussed previously, we can have the limited travel budget, which is especially true for these vehicles. This type of fixed wing aircraft has usually much more longer endurance in tens and maybe hours, tens of minutes and hours, but this is usually less. So what these problems and finding a smooth, let's say, curvature constraint path for this type of vehicles, that we need some model of or kinematic model of the vehicle that is suitable to find paths that are smooth or curvature constrained. And one of the very first, or maybe the very simplest model is a Dubin's vehicle. And because we already formulated the data collection planning as traveling salesman problem and orienteering problem, also with neighborhoods, we call these problems Dubin's, which corresponds to using this model. So what is the Dubin's vehicle? Actually, it is a non-holomic vehicle. It is for 2D. We consider X and Y, and also orientation. It has a constant forward velocity and some minimal turning radius. So we cannot turn on a spot, but we need some turning radius. This radius actually depends on the actual velocity and properties of the vehicle, but let's assume that these values are given for us. So the vehicle state is tripled, X, Y, and orientation. The position is in a plane. This is from 0 to 2p. So our configuration or state is from a special Euclidean group. So we can also describe the motion of the vehicle using the differential equation, but for simplicity we will consider some of the minimal turning radius, for example, and u as a value of 1, which simplifies the notation, but anyway, this is just scaling. What is quite important that having two configurations, which means that we have x and y and theta, and another configuration x, y, and theta, which is q1 and q2. And if we have prescribed this orientation, we can find an optimal trajectory for this type of vehicle in a closed form solution that has been firstly analyzed by Dubins, but you can also found this model as a Dubins Markov model. And furthermore, we can, without obstacles, that's the important part, and we have basically two types of maneuvers. So what we need is to make a turn along the turning radius, minimum turning radius. Then we can go straight, and then we can turn. So it will be like this in this case, let's say. And of course, it depends if these orientations are what we can do like this, or we may require some additional types. So we can firstly turn left, and then go straight, then left or right. So we have 4 combinations. But if it happens that these configurations are mutually very close and the orientations are in such a way that we can actually have to perform this CCC maneuver, which is a prolongation to actually reach the orientation. So to clear it, we have a way for this point-to-point planning with the headings. But in our data collection planning, we have a bunch of these locations, and that's probably the main topic of solving the data collection planning with Dubins vehicle. So how we can parameterize the Dubins maneuver, that is the optimal connection of one configuration with another. So this is a better plot than I will sketch. So for this CSC maneuver, and what is also, this can be 0 length, that's allowed, even for any segment. And if we have this unfortunate orientation, even though we have very close locations, the actual maneuver to reach this orientation is quite long. And as you can see, maybe if we get these locations closer, for example, we may have like this, and okay, so we will have this roughly. So this maneuver actually can be shorter than this one, even though these locations in this case are closer. So, and that's one of the challenge that is related to finding an optimal solution in these Dubin sorting problems. Because in the multi-goal Dubin's path, we have actually a bunch of these locations. And in a multi-goal, so we can have this prescribed sequence. So we have this sequence of locations, and we need to determine the headings. And just to highlight here, if we consider these straight lines, then it can actually be fed to the trajectory or path follower of the area vehicle can be fed with this straight line segments, and it will navigate or try to navigate or follow the path, but it will be less precise because it will take some shortcuts, some turns. So that's all. That's just the highlight that even for multi-rotor vehicle, it is suitable to use a smooth path such as Dubin's path. Anyway, in multi-goal Dubin's path planning, we actually don't have the sequence given, so we have the underlying TSP. Here is a recap of Dubin's maneuver properties. So for this point-to-point path with the defined heading, we can find such a solution optimally. It is the C maneuver or CCC maneuver, but the main challenge is related to the piecewise continuous function. And depending on the orientation of the headings and distance of the configurations, we have different type of maneuvers for this optimal Dubin's path. And it is shown in this cartoon where we have different type maneuvers on this right side, depending on the initial heading and the terminal heading, and here is the distance function. So we can see that if we increase the mutual distance of the configurations, we have various types depending on the initial headings. And once the distance is above the 4 times the radius, we will see that is just the CSC maneuver. So using the closed form solution, it is very fast to compute, less than a microsecond. However, this is a challenge for the optimality and finding the optimal solutions. What is the Dubin's traveling salesman problem? Similarly to the traveling salesman problem, we are looking for close, shortest, this time Dubin's path visiting each location. So we have n locations. We don't have prescribed headings, but we still need to determine the optimal sequence, how to visit this. This is the combinatorial optimization problem. But to determine the Dubin's path and to ensure that it is the shortest one, we also need to determine the optimal headings. So for each location, we need to determine the heading angle. And that's the continuous optimization problem. So we can put it together. So we are optimizing the sequence and also enumerating all possible permutations, and also enumerating the all possible assessment of the headings. And what is related to this problem, that it's mutually dependent, so we cannot find the optimal heading unless we have the optimal sequence, and we cannot assess the sequence if we don't have the optimal heading. And so that's captured here. If we have some sequence and then increase the turning radius, we can see that for some turning radius the sequence is no more optimal. And if you don't see it now, so just remind that this is a continuous domain. So it is actually very similar to the traveling salesman problem with neighborhoods. Just we use not Euclidean distance as a simplest case, but this Dubin's length of the Dubin's maneuver. So the challenges are related that this order of visits and headings are mutually dependent. So we call this problem is sequence dependent. And you can find in the literature 2 fundamental approaches, the decoupled approach and sampling-based approach, which is actually very similar to TSPN. So, but of course, if your sequence is found independently, and as you previously see in that cartoon, depending on the turning radius, it can be very, very poor. Or for mutually very far locations, the Euclidean distance is actually quite okay. And for sampling based, okay, we have continuous domain. We can sample the headings and we can transform it to this generalized TSP. But the problem is how we assure that our sampling is good, how we can sample. Now I will show you some of the approaches how to address this. And of course there are other methods, soft computing techniques, genetic algorithms, memetic algorithms, and so on. And you should not be surprised that we also deploy unsupervised learning technique to this Dubin's traveling salesman problem. So regarding some of the approaches, maybe you can consider what is the year of publication. So there is a bunch of heuristic decoupled evolutionary approaches. There are also sampling-based approaches, and I would highlight this one. So if you have mutually far locations with the given sequence, so you have a sequence of locations that are distance more than 4 rows, so we call it d4 instance, then you can use convex optimization to find the optimal headings. It is working, but still you need to elaborate. Should I turn left? Should I turn right? Should I arrive from her left to and so on. So the number of combinations you still need to evaluate is high, and it doesn't scale well. And from my point of view, to the literature, the real milestone has been with introduction of Dubin's interval problem by Gupta in 2016, because it actually provides us the lower bound, tight lower bound estimation to the Dubin's traveling salesman problem. And then we can quantify what is the quality of our solution. And we actually employ this idea of lower bound to provide informed sampling of the headings. I will show you in a minute. But in our original or data collection planning, we really like to exploit the non-zero sensing range. So we have this neighborhood, and we cannot directly use the Dubin's interval problem, but we actually propose a generalized version that actually allows us to provide similar results as for the Dubin's traveling salesman problem to the TSP with neighborhoods. So let's summarize the planning with Dubin's vehicle. We have, if we have two configurations, x, y, and theta, x, y, and orientation, we can find the optimal shortest Dubin's path analytically. But don't forget, it is without obstacles. If you need a more complex environment, then you can take a look to randomized sampling-based motion planners. But regarding the aerial mission, this is not that complicated, and there are so many scenarios and deployments where you can work without the obstacles. So the Dubin's vehicle can be constructed in multi-goal path planning, such as surveillance, inspection, monitoring missions. So surveillance and monitoring is, you can imagine it that we can find the solution and we request to periodically visit these locations. And that's actually the reason why we are looking for the closed loop, and we will have additional constraint that the arrival angle is the same as leaving angle, because we like to circulate a couple of times unless we run out of battery. And we can formulate three types of problems. The first is that we have a given sequence of locations, and we are looking for the shortest path to visit these locations, which for the Dubin's vehicle actually is the problem to find the headings of the vehicle at these locations. And we call this problem Dubin's Turing problem. If we don't have the sequence and we like to visit a set of locations in an optimal way, then it's the Dubin's traveling salesman problem. And if we have a limited travel budget and we cannot visit all the locations, and each location is associated with some reward, then we can formulate a Dubin's Dubin's orienteering problem. Okay. Let's continue with Dubin's Turing problem, because that is a fundamental building block to actually solve any routing problem with Dubin's vehicle, because in a Dubin's Turing problem, we have a sequence of waypoints and we are looking for the optimal headings. And such a sequence is a part of the TSP, but also the orienteering problem. So it is a continuous optimization problem. And as I mentioned, we may distinguish if we like to have a closed loop where we have this constraint of the same arrival angle heading as the leaving, or we can have open paths such as in orienteering problems. So we have initial location and final location, and now we can have prescribed arrival or leaving angle just because we have some airport, right? The landing site as well, which actually describe from which direction we have to approach the landing site. And this is a teeny detail that actually have some influence on the performance or the computational requirements of the finding the optimal headings. We will show that in a minute. Okay, this is that in some cases you can relax that, and so finding the closed loop with the same arrival as some leaving angle is actually a little bit more demanding, as I mentioned. And if you take a look to some literature and some proposed algorithm, you should carefully read if they are satisfying this constraint or relax that. So how we can approach it? Similarly as we did in the coupled TSPN. We have continuous domains, so we can sample that. We can create a search graph, and that's it. We can find a solution in NK cube. If we don't have the prescribed or define closed loop or prescribed arrival heading is the same as the leaving heading, we can solve it in NK square. Depending on the K, it actually affects the computation a lot. Why? Because we have here 10 locations, but the number of samples is actually, in this case, not is actually higher. And sometimes it's actually significantly higher. So the number of n is not the issue, the number of samples is the issue. And the issue is how we can sample in a good way, how we can sample the most relevant samples. And this is the example. If we can sample it uniformly. Okay, so we don't have any idea, so we can sample it uniformly. And this will provide us the solution that is using 224 samples. It provides us this feasible path. This is the blue one. And let's assume, I will show it in a minute, we can compute the lower bound. So we have this lower bound. This took us almost 100 milliseconds. If we use less samples, but we sample it more smartly, we can find solution, the blue one, which is very close to this lower bound. You can see the lower bound is tight. And we spent almost 2 times less time, but it's still insignificant. But the issue is, or the problem is, how to smartly sample that. And for that, we actually use the Dubin's interval problem that provides us the way how to compute the lower bound, and the lower bound that is tight. So what is the Dubin's interval problem? It's a generalization of the point-to-point planning of the Dubin's path. So we have defined initial location, we have defined arrival location, but instead of single value, we prescribe an interval of the leaving heading, an interval of arrival heading. And then the Dubin's interval problem is a question or the answer for what is the length of the shortest Dubin's maneuver that connect this location with that connection under the constraint that the leaving angle is within this interval and arrival angle is within this interval. And Gupta showed that such a solution can be found analytically, so it's relatively fast. It's not that fast as Dubin's maneuver because here we need to elaborate more cases, but it's still quite fast. So the solution of the dip is a tight lower bound of the Dubin's Turing problem. And one more remark, the Dubin's interval problem is not a feasible solution of the DTP, Dubin's Turing problem. Why? Because if you have these full intervals 2p, it is straight line. And it's the question if you can choose that, okay, for connecting these two locations, I will place my vehicle in that orientation. But if your airport is in this, it is not the case. Okay, I will show you in a minute. So how we can compute the lower bound? In very same way how we compute a feasible solution using sampling. So instead of sampling individual heading values, we sample the intervals and we create the same graph. And we use the same NK cube complexity to find a solution using solution of the Dubin's interval problem, DIP. And that actually provides us really tight lower bound of the DTP. Just to remark why the lower bound is not feasible. Because for this location and that location in our storage graph, we compute this solution of the DIP, DIP, Dubin's interval problem, and we can actually consider that the arrival heading is not the same as independently solve the IP for this type of problem. So the Dubin's interval problem for this part actually may consider a different leaving angle than Dubin's interval problem solution for this arrival heading. So it's not feasible solution, but it's tight lower bound. And if we take a look what we are able to achieve if we increase the computational time, and there is the number of locations, and we compute, so we can imagine that we have this iterative refinement of the resolution or the number of samples. We add more and more samples, we can actually achieve solutions with lower bound that are less than, in this case, 0% from the lower bound. And even this case is from the lower bound, so that's almost optimum. And from practical point of view, you don't care. So in this way, we can guarantee the solution quality. That's nice. And we actually employ this lower bound in this iterative refinement informed sampling way. So basically how it's working. You can consider that we start with some rough sampling. And then we compute this lower bound. Let's this lower bound be like this. And we refine this. We refine the intervals that are part of the lower bound. What is really nice on this algorithm is that it actually provides the feasible solution and also the lower bound. What is the feasible solution? So actually we can choose, if we have this intervals, let's say this one, so we can arbitrarily choose any angle within the interval of the lower bound, and then compute it for the next, use the same arrival and leaving angle. And so we can estimate the quality, and because we start with really rough, even full interval, so we can quickly find a first solution, and then the additional solution with more computational time is just improving. So we have anytime property, which is nice because the first solution is provided quickly, and if we have more time, we can improve the solution. So take a look how it can actually perform. Let's we have this iterative procedure for uniform sampling and this informed sampling. So we start with some rough constraint or with some rough resolution, and here we actually double the samples, no matter which interval. Here we will actually refine the intervals of the lower bound. And in this case, both lower bounds are the same. Here we have actually better feasible solution than for this one. But let's iterate for a while. It's almost the same. In this case, we are lucky. But this time, okay, it's better. And now we actually have almost the lower bound. This is not that tight. We have almost optimum, so there is some rounding values, and you can see that okay, if we spent this time, and if it's actually accumulated time because we use the previous resolution. So if we continue, now we have almost the same values. In this case, the lower bound is rounded differently, but what we have almost the same solution, very tight to the lower bound. Here we spend this time, and here we just sample 10 locations in this time. So if we know that we need to use some particular number of samples, this is okay. Probably it will not take 7 seconds, but we usually don't know that because it depends on the mutual distance and so on. So this is the very intuitive way how we can inform the refinement, the sampling using the lower bound. And if you take a look what is the scale, how these approaches scale, the uniform and inform, you can see that the uniform doesn't reach these very close solutions to the optimum. So from practical point of view, this is it can be considered as optimum. It's very close to the lower bound, and it is enabled by this inform sampling. But in our Dubin's traveling salesman problem, we don't know the sequence. So the Dubin's ring problem, we show that we are able to solve it or to find a very high quality solution. But the question is how we can employ it in our Dubin's traveling salesman problem, because we need to elaborate the sequence and also the headings. So it is a combined sequencing part and continuous optimization. But before we will go to some other methods, let's start with very intuitive and one of the very first heuristic algorithm, which provides us some approximation factor actually, but it's not that great. But basically the idea is that we find the sequencing part relaxing the motion constraint that is a solution of the Euclidean distance, or Euclidean TSP using the Euclidean distance. So now what we need is that we need to establish headings for even edges. Okay, that's we can just connect them by this straight line, which actually defines this leaving angle defines the arrival angle. And because we did for even edges, we have these in this direction. So we have this leaving angle, this arrival angle for this leaving angle. So we can compute the Dubin's maneuver, and that's it. It's not that great, but it's super fast. So if we have a sequence of visits, we don't need to use such a very intuitive, very naive algorithm. We can use the solution of the Dubin's ring problem, and we can see that we can do that. We can find a very good solution. Okay, that's what we showed previously, and the question is the same. So how to sample the headings? More samples make finding more demanding. What is the solution quality? Tight lower bound. We already have it. So if we put these things together, this is the DTP. It's iterative refinement. And what is interesting is the memetic algorithm that actually optimizes both parts. There is also local iterative optimization. I will show you later, which is incremental iterative optimization, high climbing method. And we have this naive alternating algorithm. And if we take a look, these are performing poorly. Quite surprisingly, the memetic algorithm actually optimizes sequence. And we can see that there are some cases that the sequence really matter, but the solution of the DTP in the memetic algorithm is poor, while in this approach, we use this tight lower bound to inform the sampling, and we provide, we get very competitive results. It was quite promising. So now what we can also do, we can sample the headings uniformly in this case, and consider this generalized traveling salesman problem. Here it's definitely asymmetric TSP because it depends on the orientation. direction how we approach the location, and you already know how to transform GTSP to asymmetric TSP, and then you can transform it to TSP. Here actually the distances are depends on the optimal connections between the configurations with the headings, so it's not Euclidean distance. Let's continue with Dubin-Stroman-Axelsen problem with neighborhoods. It is a very intuitive extension. Instead of locations, we have regions. We still need to determine the permutation, the sequence, headings, and also the locations. And of course, we have just a single location, or we have this disk. We can actually encode the position of the waypoint on the disk by a single variable, but still we have these headings. So if you remember how we approach the traveling-Axelsen problem with neighborhood, is very similar here, but we always has this heading and Dubin's path instead of, for example, Euclidean distance. What are the approaches? Not surprising, the coupled approach. Okay, you can solve this, find the sequence. Here we can actually use the sequence found as the Euclidean TSP. Right. We can also sample. It will be a little bit more samples because we need to sample the headings, and for each location inside a neighborhood we need to sample the headings. So sampling base. There are soft computing techniques that encode the solution and somehow permute it, like the memetic algorithm and supervised learning. So we also like to have the lower bound, and we use the Dubin's interval problem for lower bound of the Dubin-Stroman-Axelsen problem, but in this neighborhood we actually need generalized Dubin's interval problem. But first take a look to the decoupled approach. We find the sequence, and as I mentioned, we can sample the locations, and for each location we sample the possible headings. So the search graph is the very similar, but it is larger because we need to sample the location, and for each location we need to sample the headings. So it quickly grows and it will be more and more demanding. Or as an alternative, we can actually utilize this local iterative optimization, which basically assume that we have a sequence of goal regions, and then we iterate, and for each iteration we independently optimize headings and position, and we then check the local minima. So as we have some loop over the regions, so we first optimize heading, so we have some location and we optimize the heading. Okay, the optimal heading regarding this location and that location will be this. Now we optimize what will, for this heading, what will be the position, so it will be probably this, because it will provide a shorter Dubin's tour, this one, and instead of previously this one. So very straightforward, surprisingly quite well performing, but we still need to assess the quality, and we need this lower bound. And for that we cannot use the Dubin's interval problem because it's not sufficient, because we have this 1 degree of freedom in this region, and therefore we formulate the generalized Dubin's interval problem, which is an extension of the Dubin's interval problem. So we again have a interval, prescribed interval, leaving interval, and arrival interval, but instead of single location we have a region, and we are asking what is the length of the optimal Dubin's path from this region to that region under the constraint that leaving heading is within this interval and arrival heading is within this interval. This is very challenging, but actually Peter Vanya proposed that we can transform this full problem to one side problem where we actually have just single location, and here we enlarge using Minkowski's sum the goal region by the region of the initial region. And Peter also showed that this the optimal solution is actually one of 7 cases, And for these 6 cases, we have closed form expression. The 7th case, we don't know if there is a closed form solution, but it can be solved using convex optimization, and it is relatively quick. So regarding the implementation that you can actually download, is the Dubin's maneuver. This is just this. It takes, on the same platform, it takes less than a microsecond. For the Dubin's interval, if we have this, it takes roughly 1 microsecond. But for the generalize, we need actually elaborate more cases, because here we actually use the Dubin's interval problem. It is more, but still a microsecond. So now we can be satisfied, but if we take a look to the very same schema as we use for the Dubin's traveling salesman problem with Dubin's interval as a lower bound, in here for the Dubin's traveling salesman problem with neighborhood for a given sequence, and then we can perform this very similar refinement. So we have a resolution 4. The 4 is, so we split the region to 4 intervals like this. And then within this interval, we have the heading intervals. We have the lower bound. This is the red. Now it's clearly unfeasible, right? And we have this gap. So we add the resolution. Okay, it's reducing. It's almost the same shape. And we future refine. So this gap, 9 seconds, 43 seconds, 1%. So 10 regions, but it's more demanding. It's not seconds, milliseconds, only seconds, because it's tens and hundreds of seconds and doesn't scale as the Dubin's traveling salesman problem, because this is more demanding. But we have estimation of the solution quality, and that's the take-home message. There is a method that you can use to assess your solution by lower bound, and say, okay, I am within the distance of this lower bound. So if this is 1% and I'm fine with 1%, that's okay. So this is some show how it's actually performed with increasing resolution. That is the number of intervals, what is the computational time, and what is the relative length. So we see that the complexity of the algorithm grows with the almost k cube, which is relatively nice. But these hundreds of seconds is not that nice, depending on the of course on the problem. But the lower bound and upper bound, we see, okay, we are getting closer. So somewhere here there will be the optimum. So having the solution of the Dubin's Turing problem, solution of the Dubin's traveling salesman problem, and solution of the traveling salesman problem with neighborhoods, you can ask what is the extension of orienteering problem to Dubin's vehicle. And this has been actually introduced to the community by Robert Penička, and surprisingly, there was no such a previous approach, so we believe this is one of the very first, and it is motivated by deploying these area vehicles in a scenario to capture some locations of interest, but we cannot capture all of them. There is a limited travel budget, so we need to consider the selection of the most rewarding locations where there is something really interesting. So that's the motivation, and also during this work we actually consider that it is important to directly solve the Dubin's orienteering problem. And what is the formulation? So we have curvature-constrained data collection path that respect Dubin's vehicle model with minimum Turing radius and constant forward velocity. Okay. So here we also need to, as similar to the Dubin's to the orienteering problem, we also need the subset, the sequence to ensure Tmax, and the headings. So. And actually, once we have a sequence, once we have a subset, and the sequence, the optimal headings can be actually solved by the DTP. That's the reason why we consider Dubin's tuning problem important in this type of applications. And what we actually apply is a variable neighborhood search, which is a general meta heuristic for combinatorial optimization routing problems. We already mentioned that. So there is a shake and local search procedure. This neighborhood is actually the set of solutions that we can create from some incumbent solution applying some of these operators used in shake or local search procedure. The variable neighborhood search for the orienteering problem has been proposed in 2006, and what is the main difference is that we actually have, for DSP, we have this incumbent solution as a vector of location we like to visit, but here we have a limited budget, so this is a part of this vector that is within this Tmax budget. So how it is used, so we use some improving heuristic as like cheapest insertion for finding the initial solution. We have the a set of predefined neighborhoods that are these operators like insert, exchange, path, insert, pass, exchange. We already mentioned that, but instead of systematical applying of all operators, we actually use the randomized variant of the variable neighborhood search that we examine only square changes in local search procedure in each iteration, which is actually this very same we discuss in data collection planning. So here are some examples of solution. Of course, that is a little bit more demanding regarding the needed distance than the Euclidean distance, regarding the travel cost, but principally it works the same. And you can notice what is the computational time for this very first VNS-based solution. And if you remember that for the graphs method, for example, even for the orienteering problem with neighborhood, this was significantly less demanding. We already discussed that Dubin's orienteering problem can be addressed by variable neighborhood search, but we can ask if it is really needed to address Dubin's orienteering problem directly or explicitly, because we can use the Euclidean orienteering problem. We can determine the solution, and then from the solution we can determine the Dubin's path. If this path is exceeding the travel budget, okay, then we need to reduce the travel budget here, and then we can iterate. It will provide us some solution. Or we can just don't do that. We can follow these straight lines. We actually did it. And depending on your trajectory follower, it may happen that the trajectory follower will miss some of the locations because of sharp turns. And it of course depends what is the controller. In our case, it's optimal trajectory follower using model predictive control. And you feed it with some locations, and it tries to keep it on the track. But if there is a sharp turn, it's actually like a shortcut, which is probably visible here. So there is a need to actually solve the Dubin's orienteering problem. So what we know, okay, so variable neighborhood search is one of the options. We already discussed that. We also know that orienteering problem, especially OPN or COPN, can be addressed by the unsupervised learning, and the headings is nothing else than some sort of the neighborhood. So we also deploy the unsupervised learning, and if we take a look what is the solution quality, which is captured in this plot, that probably the highest, here we are maximizing the reward, so the highest reward is by the variable neighborhood search. But we also experience that it is more demanding. So depending on the computation time you have, so you can find good solutions with more time, or you can use this simple heuristic unsupervised learning to find, in some cases, not that significantly bad solutions, but in less computation time, and it depends on the application. And regarding the neighborhood, so of course we can extend the Dubin's orienteering problem to neighborhoods, where we further, in addition to the subset, sequence, locations, we have the headings. So this is more continuous domains. And again, you can consider, okay, I can sample the headings, I can sample the locations for each location, the headings, and solve it as a discrete variant. But you can also use the variable neighborhood search, and this is variable neighborhood search to the Dubin's orienteering problem. And this just basically capture the initialization and application of the shake and local search. Within the local search, we actually perform the n-square options. But what is here, how we consider this neighborhood layer, so for the shake and for the local search. So you can find the details in the paper if you're interested. But what I would like to say is that actually we can introduce the continuous optimizations. We can consider these operators as a continuous optimization because we have this DTP underlying. So instead of sampling, we can actually determine the headings for a particular sequence as a part of these operators, and that actually improved the performance. But to show some examples how this shake operator on a discrete variant can work, so here we actually move some subset to another different location and check for the solution, and we can exchange and so on. And based on the exchange, we have a new sequence, and we can determine the headings using the solution of the DTP. And the DTP can be solved by sampling, or if you remember, there was the local iterative optimization. That's also something that you can use. And it is particularly not that important that you know all these details, but the take-home message is that you can sample the continuous domain and solve it as a discrete problem using, for example, this meta-heuristic variable neighborhood search. Or you can introduce some of the results from this Dubin's Turing problem, from this continuous domain, and speed up and use this where it is needed. So for sequencing, you need to elaborate the combinations. For headings, you may not need it. For locations, okay, this local iterative optimization also is able to solve using local optimization the headings and locations. So that is the take-home message. And here is just an overview of performance of these existing 3 years old approaches. I can see that the variable neighborhood search is providing the best solutions. Albeit on the other hand, it is quite demanding, at least for this implementation, and the unsupervised learning is less. This is very inaccurate, and it is relatively fast. And here is some demonstrator to show that this is not just for virtual computation, but we also deploy these algorithms to real platforms. So this is a pre-compute solution, and then it is deployed on the robot. Of course, that is not super straightforward. Okay, so it is straightforward, but it means that Once you have this solution, you need to pass this solution to this trajectory follower, and you need that trajectory follower. But once you have this pipeline, it is relatively straightforward to deploy the solution you compute prior to deployment. It's another video. You can see the drone here. It's relatively small, so performing the overflight on the object of interest that are pre-selected based on the expected reward. Okay, if you like to know more, take a look to the paper and also to this link. Finally, the very end of this lecture, I would like to show you some extensions and examples of the generalizations of these problems. And maybe you may ask yourself, okay, Dubin's vehicle is nice, we have a really nice theoretical results, we can solve this Dubin-Strings problem, traveling acceleration problem, orienteering problem, but it is in 2D. How about 3D? So there is another model which is relatively simplified, and that's called Dubin's airplane model. And in addition to the orientation, we also have a constraint on a pitch angle. So that defines some climbing angle and some diving angle. So, and you cannot arbitrarily choose that, even though within this Dubin's airplane model, what is allowed is that if you reach some location, you can immediately change the pitch angle, which is okay for some vehicles, but for some vehicles it's not feasible. And again, it is possible to formulate a full constraint, but it will be more demanding. Regarding this actually hasn't the closed form solution. So it is relying on a numerical optimization. And basically we have let's say 3 types of maneuvers. We have some very far locations with different with different altitudes. So if the locations are at the same altitude, it is actually the Dubin's vehicle. But if we have very small change of the altitude and the locations are very close, so we need to actually perform some maneuver. It's not that interesting. But if you have very close in 2D projection maneuver locations, but it is at different altitude, significantly different altitude, you actually need to perform this helix spiral to actually reach it. And what we can do with the Dubin's traveling system problem with neighborhood in 3D, basically we can follow the approaches, decoupled continuous optimization. And if you remember this local iterative optimization, we can also do that, but we need to parameterize the position on the 3D regions. So these are the 3D regions. So we can consider sphere, we can consider ellipsoid, and we can define angles that define the waypoint on this region, ellipsoid region. And if you consider, okay, in this local iterative optimization, we use it to optimize the heading, we can also optimize the position in the disk. It was also the angle, and these are also the angles. So it is within the same domain of the 2 and 2p, and you can independently optimize that, and it will provide you some solution. So this is the local iterative optimization based solver for 3D Dubin's traveling system problem with neighborhood. It's relatively straightforward. There is one key point that you can actually consider. You can take a look to this paper, and that is that you can actually improve the solution using not using the Euclidean distance of the TSP, but using other, considering the 3D, the altitude changes. But I'm not intended to go to the details. I would like to show you that, okay, even that this sounds relatively complicated, this is the cartoon that shows that we can, this is the real computational time. So within less than 1 second, we using this approach, we can find a solution. And for this type of demonstrator, I would like to show, okay, if you're if your deployments requires fast replanning, and your algorithm is fast, so you can deploy it, because this is fast enough. Of course, depends on what is the mutual distance and so on. But these provide you some ideas how these problems can be extended for this type of aircrafts, fixed-wing aircrafts. But maybe you also ask, how about the multi-rotor drones? Because the multi-rotor drone is not limited by limited turning radius. It can move arbitrarily in any direction. Yes, it is true, and it is actually limited only by maximum velocity and maximum acceleration. And for that, you have to really exploit all the possibilities. You actually need a sufficiently general parameterization of your trajectory, of your curve. And what we did is that we construct Bezier curves. Bezier curves, and we deploy unsupervised learning. That's not that surprising, but this type of problem is relatively complex. You also need to estimate the travel time, so you need to determine the velocity profiles. And we are able to solve this problem to visit, this is variant of TSPN. I will not say Dubin's, but Curvature-Constrained TSPN with Bezier curves. The curvature constraint is a little bit tricky here, but it is in the end it is a smooth path because it's Bezier curve. Provide us the way how we can optimize the trajectory along which we compute the velocity profile, and this velocity profile satisfy the acceleration limit and maximal velocities. But here we don't have any theoretical results on the solution quality. So what we usually do is that we take a look to the velocity and acceleration profiles, and we saturate the vehicle. So most likely the vehicle is reaching its limit. What we also did in a very similar fashion, we deploy the unsupervised learning with these Bezier curves to multi-vehicle curvature-constrained team orienteering problem with neighborhoods. And as you can see, how the drones are able to actually follow the planet trajectories. Here is still unanswered, unaddressed, unaddressed problem, because we deploy them. We plan the mission. Then we deploy it on the robots. There is a collision avoidance system, and if there is a detection of the collision, one of the vehicle makes a avoiding maneuver, which actually takes some time, and then the optimal trajectory forward tries to reach the previous plan, but it is out of time because it needs to land in defined time, and it misses the location. So it is still the open question how to find a robust plan to such disturbances. So now let me summarize. I show you what is data collection planning with curvature-constrained paths, trajectories. Paths and trajectories, why? At this very end, it's because for the Dubin's vehicle, we have constant velocity. So we immediately have the time. I show you how you can extend the TSP and orienteering problem with Dubin's vehicle, how you can address the problems with neighborhoods. Important point is that I show you Dubin's Turing problem as a fundamental part of any sequence routing problem with Dubin's vehicle, which you can find in TSP and OP. I show you that there is a Dubin's interval problem that can provide you a tight lower bound, and there is also a generalized Dubin's problem that can provide you tight lower bound for Dubin's Tronik-Salzman problem with neighborhoods. So it's n here. And of course, it still holds for any these type of problems that you can sample the continuous domain and consider it as a discrete combinatorial optimization. But here it is a little bit more tricky, because even that you increase the number of samples, you will actually not found the optimal solution, and you can still be very, very far. And just one of the example is if you have your locations exactly on the circle with the minimal tuning radius, there is only just a single heading that will provide you the optimal path, and it is not you are not approaching it because it's a single value, so it's something like this, and this is the value. Otherwise there are these CCC maneuvers. So so it can be a little bit more tricky, and that's why it is important to have this tight lower bound. So thank you for your attention, and we will continue on the sampling based motion planning in the following lecture.